Hello guys, so welcome to the session on problem solving with logic design. What exactly is logic design? So the term logic design has two words in it. One is logic and the other one is design. So we know that the logic never changes. In 70s also 2 plus 2 was 4 only. Now in 2023 also 2 plus 2 is 4 only. So that means that logic never changes. But what keeps on changing is design. Earlier in 70s we had CPUs of this room big size. Okay, so nowadays we have CPUs which is very smaller, very thinner. So that means that logic remains the same, okay, but the design keeps on changing. So this is the idea what we use in logic design. So logic design is a very important topic that we need to understand to be very successful in the digital era. So we'll start off with something called as principle of duality or duality theorem. So principle of duality. So what exactly is principle of duality? See, principle of duality states that every theorem or algebraic expression of a Boolean algebra it is transformed into one more theorem or algebraic expression is transformed into one more theorem or Boolean expression or algebraic expression provided we interchange first one, wherever you have plus you interchange plus with dot, okay. Then wherever you have 0 you interchange 0 with 1 and vice versa. So this is the principle of duality, okay. Now we know that in Boolean algebra we know that x plus x bar is equal to 1, okay, where plus represents a sum term, dot represents a product term, okay. So now whenever we use the principle of duality, one Boolean expression or algebraic expression, okay, it is transformed into one more Boolean expression. How it is transformed? See, wherever you have plus, you replace plus with dot. You can see x as it is, plus is replaced with dot. And wherever we have 1, replace it with 0, or wherever we have 0, replace it with 1. Okay, so this is 0. Now we know that the dual of x plus x bar is equal to 1 is always true. That is, x into x bar is equal to 0 is also true. Okay, so x into x bar is equal to 0 is the dual of, this is the dual of x plus x bar is equal to 1. Similarly, we know 0 bar is 1. Okay, so this is a very common formula. Okay, 0 bar is 1. Okay, so we know that if we use principle of duality, okay, wherever we have 0 we'll replace it with 1, wherever we have 1 we'll replace it with 0. That is 1 bar is 0, so that is always true. So this is basically what we call as principle of duality. So now let us do a little bit of problem solving on this, okay, because without knowing this it is not easy for us to do simplification. Okay, so if the question is write the duals of the following Boolean expression. So let us take one example. So a plus b plus ab is equal to a plus b. So if you want to write the dual of a plus b plus ab is equal to a plus b, now we know that the principle of duality is wherever you have plus, replace it with dot, wherever you have dot, replace it with plus, wherever we have 0, replace it with 1, wherever we have 1, replace it with 0. Now with that, a dot b dot, so you have a dot b, this is a plus b, this is equal to a into b. Okay, so that means that this is the dual of a plus b plus ab is equal to a plus b, so which is always true. Okay, similarly you can take any similar expression and it is easy for you to prove that the dual is always true. Okay, so let us now continue. So now let us take one more example. Okay, so let us say a plus b plus a bar b bar is equal to 1. Okay, so if you want to write the dual of this, wherever you have plus, replace it with dot. Okay, wherever you have dot, replace it with plus, wherever you have 1, replace it with a 0, and wherever you have 0, replace it with a 1. Okay, so this is basically the dual of this. Okay, dual will always be true. Okay, so that is a into b into a bar plus b bar is equal to 0. So let us prove this. Okay, if you take the left hand side, that is a b into a bar plus b bar, this should give us 0, right? So if you multiply a b into a bar plus a b into b bar, so we know that a bar is what? A bar is 0, b bar is 0. Okay, so that is 0 plus 0, which is nothing but 0. So this is equal to RHS. So thus we have proved that the dual is always true. Okay, so now the next thing what we have to understand, basically to start simplification, is to know about the logical operators or the basic gates. Okay, so let us now know about the basic gates or logical operators. Okay, now basic gates means using these gates we should be able to construct every other gate schematic, okay, or every other gate. So that is why it is called as a basic gate. So we have 3 basic gates in logic design. The first one is a NOT gate. Okay, the second one is a AND gate, and the third one is a OR gate. So what is the logic of the NOT gate? The NOT gate is called as a invert gate. Okay, NOT gate always inverts the logic level of its input. Okay, NOT gate inverts the logic level of its input. So how do you see a NOT gate? Means NOT gate is a single input gate. It is represented, okay, like this. So if your input is A, your output will be A bar, Y being the output. Okay, so A and A bar, if you have a single input, you have, okay, so 2 power 1 input combinations. Okay, so that is 0 and 1. If your input is 0, your output will be invert, that is 1. If your input is 1, the output will be 0. Okay, so this is basically the logic what we use in NOT gate. Then coming to AND gate. Okay, AND gate is always called as the product gate. Okay, AND gate is called as the product gate. So what is the logic of your AND gate? See, the logic of the AND gate is the output of the AND gate is high if and only if all the inputs are high. So that is the logic of your AND gate. So be it 2 input AND gate or 3 input AND gate or 4 input AND gate. Okay, so whatever input AND gate it is, the logic will remain the same. Logic will never change. So that I had told you at the beginning of the session itself. Okay. So now, if I see the AND gate, here in case of AND gate, output is 1, output is at logic 1. Okay. If and only if all the inputs are at logic 1. Okay. Now, if you take a 2-input AND gate, 2-input AND gate is represented like this. Okay, 2 inputs A and B with the output Y, which is nothing but a product term A into B. Okay. So, if A and B are inputs, 2 power 2 input combinations. So, that is 0, 0, 0, 1, 1, 0, 1, 1. Okay, when will be the output 1? Okay, only if all the inputs are at logic 1. Only this will be 1, rest of the things will be 0. So, this is how AND gate works. Okay. Lastly, OR gate. OR gate is a sum gate. Okay. The whole logic design just depends on these 3 gates: NOT gate, AND gate, and OR gate. Okay. The whole gist is in this only. Okay. So just understand that OR is represented with a plus symbol, AND is represented with a dot symbol. Okay. NOT is represented with an invert symbol. Okay. So if you look at your OR gate, okay, the OR gate, the output of the OR gate is at logic 1 if at least one of its inputs is at logic. Okay. So that is the logic of your OR gate. So at least one of its inputs is at logic. So this is how we take OR gate into account. Okay. So if I have 2 inputs A and B, output Y is equal to A plus B. Okay. So this is how we represent a OR gate. A and B are the inputs. Y is equal to A plus B. So 2 inputs, 2 power 2 input combinations. Okay. So the output is 1 if any of its inputs is at logic 1. Only this will be 0. Rest of the things will be 1. So this is how OR gate works. Okay. Now if you look at the Boolean formulas or theorems, okay, if you look at the Boolean formulas or theorems, okay, so we know that there are a lot of Boolean laws or theorems, but let us understand it slightly differently. Okay. Differently means we know that every Boolean formula or theorem has different operations. Different operations in the sense OR operations are there, AND operations are there. Okay. If we know only one type of operation, the other type of operation, okay, is easy. How? Because we know that the dual is always true. Okay. If I say OR operation, AND operation is always the dual of OR. If I say AND operation is always the dual of OR operation is always the dual of AND. Okay. So that's how we can make things more easier for us. Now let us see some OR operations. Okay. So looking at the Boolean formula, some OR operations are there. Which are the OR operations? Okay, A plus 0 is equal to A. This is one OR operation. Similarly, A plus A is represented as A only. Okay. Then A plus 1 is 1. Then A plus A bar is equal to 0. Some of the OR operations I have written. See, I have not written any AND operation because we know the dual of OR is AND and it is always true. So now let us find the dual of this, okay, according to the principle of duality. So if you find the dual of this, looking at the AND operations, okay, so wherever you have plus, replace it with dot, vice versa. Wherever you have 0, replace it with 1, vice versa. So now accordingly this will become A into 1 is equal to A, correct? Because plus is replaced with the dot, 0 is replaced with 1. Okay, so this is A into A is equal to A. Okay, a plus a is equal to a was there. A into a is also a only. So then a into 0 is equal to 0. A into 0, a dot 0 is 0. Similarly, a dot a bar is equal to 1. Okay, a bar, sorry, a plus a bar is equal to not 0, a plus a bar is 1. Okay, so if you find the dual of this, a plus a bar is equal to not 1 but 0. Okay, so 1 second. So like this, what you can do is, by finding the dual of OR operation, you can easily figure out the AND operation. Similarly, by finding or by knowing the AND operation, you can find the dual of the AND operation and easily figure out the OR operation. Okay. Now, how to check whether this is true? Anyway, we had a simple mistake here. Okay, but let us see whether what we have done is true or not. Okay, what we have done is correct or not. Okay, how to check? We can prove this. Okay, how we can prove? See, you take this formula, you substitute a is equal to 0 in the equation. If you substitute a is equal to 0 in this equation, 0 plus 0 bar is equal to 1. Okay. So let us forget about is equal to 1 because this is RHS. 0 plus 0 bar. 0 plus 0 bar is 1. Plus means we know it is a OR gate. Okay. In the OR gate, what is 0 and 1? We know 0 and 1 is 1 only. Okay. So LHS is equal to RHS. It works. Okay. One more. Okay. To prove that this is true, then substitute A is equal to 1. Okay. So LHS is equal to, okay, so that is A is 1 plus 1 bar. Okay, what is 1 plus 1 bar? That is 1 plus 1 bar is 0. Okay, 1 0. Okay, plus means OR gate. Okay, it is a sum term. Okay, so 1 0 is always 1 only. Okay, so thus it is proved. Okay, it is very easy. You just need to substitute the value of A is equal to 0 and A is equal to 1. In both the cases, you check your the truth table of your OR gate. Okay, so it should be appropriate. Similarly, you can check on the other side also. A into A bar is equal to 0. Okay, so substitute A is equal to 0. Okay, so in the first case, so if you take the LHS, 0 into 0 bar. Okay, so that is nothing but 0 into 1. Okay, into means this is a AND gate. Okay, into or dot what we call. So dot is basically referred to as a product gate. Okay, 0, 1. What is 0, 1 in an AND gate? Okay, so only in an AND gate output is 1 if and only if all the inputs are 1. Okay, so 0 and 1 is 0 only. Yeah, correct. This is RHS. Similarly, substitute A is equal to 1. If you substitute A is equal to 1, 1 into 1 bar. Okay, that is 1 into 0. What is 1 into 0 in your AND gate? It is 0 only. So that is RHS. So thus it is proved. Okay. Now whichever Boolean formula you take, that Boolean formula you can always verify. Okay, provided you substitute the variable with either the value of 0 or value of 1 and check with respect to its logic gate the output with respect to the truth table. Okay, it should always prove to be correct. Okay, so moving on. So now what we will do is we'll write down a few more Boolean formulas for your understanding before we start solving some type of problems. Okay, so now so writing some more Boolean formulas. So you know that according to the commutative property, so A plus B is equal to B plus A. Okay. Now you find the dual will always be true. I will straight away write it. A into B is equal to B into A. So if you want, you can find the dual. No need to mug it up. Okay. So then similarly you have this associative property. A plus B plus C is equal to A plus B plus C. Similarly, on the other side, A into B into C is equal to A into B into C. Okay. Similarly, you have this distributive property, that is A plus BC is equal to A plus B into A plus C. Similarly, the dual of this, that is A into B plus C is equal to AB plus AC. So this is also true. Okay. So you have some more formulas like A double bar is A. Okay. And De Morgan's law, A plus B whole bar is equal to A bar into B bar. Okay. Similarly, A into B whole bar is equal to A bar plus B bar. Okay. So all these formulas, okay, do hold good. Okay. And there is one more important formula which I want you people to remember. So that is A plus A bar B is equal to A plus B. Very important formula. Very commonly we use this formula. Okay. So if you want to check the validity of this particular statement, what you do is you construct a truth table. Okay. You construct a truth table and you can easily figure out what we have written is correct or not. Okay. How to construct a truth table? So A, B, okay, we want A bar. Okay. Then we want A bar into B. So then we want A plus A bar into B. So then we want A plus B. Okay. So 2 inputs, 2 power 2 input variables, 0, 0, 0, 1, 1, 0 and 1, 1. So A bar 1, 1, 0, 0. So A bar into B. Into B means it is a AND gate. Only 1, 1 will be 1. Rest all will be zeros. Okay. So now A plus A bar B. Okay. A plus A bar B. 0, 0 is 0. Okay. You are looking at OR gate. 0, 1 is 1. If any of the input is 1, the output is 1. So then 1, 0 is also 1. Okay. Again 1, 0 is also 1. So we got 0, 1, 1, 1. Okay, on the other side, okay, this is LHS. Okay, this is RHS. Okay, so what is RHS? A plus B. Okay, A plus B means, okay, so it is a sum term or a OR gate. So if you look at your OR gate, so now you can see in the output of the OR gate is, okay, A, B, okay, A plus B. So it is also 0, 1, 1, 1. Okay, so you can see both the outputs of LHS and RHS are same. So that is how we can prove that A plus A bar B is equal to A plus B. So these are some of the important formulas you need to remember to simplify. Okay. Now you can ask me, sir, what is the advantage of doing simplification? So is it really necessary to simplify? What exactly is simplification we are talking about? Okay. When we are talking about simplification, we are trying to reduce the number of literals. What is number of literals? Okay. So let us take an example here. I'll say simplify using Boolean formulas. Using Boolean formulas and theorems. Okay. So let us take a small example. So I have A bar, B bar, C bar plus A bar, B, C bar plus A bar, B, C. So I need to simplify. So what exactly is simplification here? Now let us understand here. Okay, so there are total of 9 literals. Okay, literals means, okay, each one, A bar is a literal, B bar is a literal, C bar is a literal. Okay, A bar, again A bar is one more literal, B is one more literal, C bar is one more literal. So total there are 9 literals here. Okay, now what exactly is simplification? The meaning of simplification is reducing the number of literals. Okay, now you can ask me, sir, if I reduce 9 literals in this case to 8, is it simplification? I will say yes, it is simplification. Okay, so if you have a chance of further simplifying, okay, you can reduce, okay, 9 literals to 3 literals also. Okay, 2 literals also. So that exactly is simplification. So if you reduce 9 to 8, I am not telling that it is wrong. Okay. So it is correct only, but it is not perfect. That's all. Okay. Now what happens? You can ask me, sir, what happens if I simplify? If you simplify or if you reduce the number of literal, the hardware circuit, or in other words, the design what we are talking about with respect to logic design, the design will automatically come down. Okay, that is, you will start seeing your hardware, okay, so much more smaller in size. Okay, so it looks, okay, better. Okay, so compared to more number of literals or your hardware circuit with more number of literals, that is the biggest advantage what you get. Now, if you want to simplify this, what you can do is start applying Boolean formulas. Okay. So now what you do is, in these two expressions, take A bar C bar as common. If you take A bar C bar as common, you are left with B bar plus B. Okay. So plus A bar B C. So what is B bar plus B? Okay, B plus B bar is equal to 1. Okay, so we know that B plus B bar is equal to 1. So because B plus B bar is equal to 1, okay, so you can write this as A bar C bar plus A bar B C. Okay, so now you take A bar as common here, C bar plus B C. Now can we stop here? How many literals we have? We have 4 literals. Okay, so now can I stop here? No, I can apply one more Boolean formula. What is that one more Boolean formula? Okay, C bar plus BC, we can write it as C bar plus B. Okay, according to the previously proved formula, I told you A plus A bar B is equal to A plus B, right? Similarly, we can write C bar plus CB is equal to C bar plus B. Okay, so now you can further reduce this as A bar into C bar plus B. Okay, now you can ask me, sir, can I keep the answer as if I multiply A bar C bar plus A bar B? Okay, now the answer is very simple. This is 3 literals and this is 4 literals. Okay, so 3 is always better than 4 literals, so it is obviously, okay, good to stop at this particular stage. So we'll discuss 2 more examples and then we'll stop the session. Okay, so now let us take a much more trickier problem to solve. Okay, so xy plus xyz plus xyz bar plus x bar yz. Okay, so now here you know that xy is common in this also, this also, this also. If you take xy as common here, it is 1 plus z plus z bar plus x bar yz. So we know that 1 plus a, okay, 1 plus a is what? 1 plus a is, according to the Boolean formula, 1 plus a is 1. Okay, 1 plus anything is 1. So now here xy into 1. So the whole thing 1 plus z bar, no need to simplify z plus z bar and then continue. So you can write it as xy plus x bar yz. Okay, so now you take y as common here, it is x plus x bar z. Okay, so we know that x plus x bar z is equal to x plus z. So you can further write it as y into x plus z. Okay, so this will be your answer. Okay, so if you want me to take much more complex problem, we'll take one complex problem and we'll end this session. Okay, so let us take one complex problem and try to solve it. So x plus y into x bar into y bar plus z bar whole bar plus x bar y bar plus x bar z bar. Okay, just by seeing this you will not be able to figure out what will be the output. Okay, applying proper Boolean formulas at each and every step, then only you will be able to figure out what will be the correct answer. Okay, so So now we know that x bar into y bar plus z bar whole bar. So this is of the form a into b whole bar. Okay, that is your De Morgan's law. So De Morgan's law says a into b whole bar is equal to a bar plus b bar. So apply this formula. So x plus y into a into b. I will say this is one expression. A I will say. This is b I will say. Okay. So that is x bar plus y bar plus z bar whole bar plus x bar y bar plus x bar z bar. So you should be very slow and steady in solving these things because you can go wrong at any point of time. Okay. So now x plus y into, we know what is x double bar. Okay, double inversion rule, x double bar is x only plus, see, x double bar is x, okay, plus y bar plus z bar whole bar. So that is a plus b whole bar is equal to a bar into b bar. This is also De Morgan's formula. So let us write this as, okay, y bar plus z bar whole bar is y bar into z bar. So plus x bar y bar plus x bar z bar. So this is x plus y into x plus yz, okay, plus x bar y bar plus x bar z bar. Okay, so this is x plus, okay, you can multiply. So this will be xy plus this will be y into y will be y only, y into y will be y only. So I will write yz as yz only plus x bar y bar plus x bar z bar. So now what you do is take x as common. If you take x as common here in the first two, okay, if you take x as common, 1 plus y is 1 only. So x into 1 plus y, so this will be x only plus, okay, so I will pull x bar y bar and x bar z bar to the front and I will push yz to the back. Okay, why? Because we know commonality is better. So x bar y bar plus x bar z bar plus yz. Now if you take x plus x bar y bar, x plus x bar y bar is x plus y bar. Okay. So now again you can apply that formula. So this will be x plus y bar plus x bar z bar plus yz. Okay. So now you take x plus x bar z bar. So this you can write it as x plus z bar plus this and this together. Y bar plus yz, you can write it as y bar plus z. So you can write it as y bar plus z. Okay. So now you can rearrange this x plus y bar plus z bar. So we know what is z plus z bar. So z plus z bar is equal to 1. Okay. So that will be x plus y bar plus 1. So 1 plus a is equal to 1 only. 1 plus anything is 1. So at the end of the day, your answer is 1. Okay. See, this is how you have to tackle these type of problems. Okay. Like this, you can always do problem solving, much more interesting problem solving with respect to logic design. Okay. So logic design is basically problem solving. If you understand the concepts very well, the problem solving will be much more interesting and much more curious for all of you. Thank you guys. So thank you so much.